This problem is example 2.2-3 from the textbook Conceptual Dynamics. The problem statement reads, a car is driving along a straight road at 60 miles per hour. The driver suddenly applies the brakes, decelerating the car at a rate of a, the acceleration equal to the negative of the square root of the position s, where a has units of feet per second squared and s has units of feet. What is the stopping distance of the car? This is again a rectilinear problem for a particle. It's rectilinear in the sense that the car is traveling in a straight line in one dimension. It's not curving or anything like that. And even though a car inherently is not a point mass, we will be able to model it as such for the purposes of this problem. When we solve a problem, again, the first step that we always take is to read the problem and try to understand what's happening. We may draw a picture to help us in that case. May not be necessary in this case, but we can sort of imagine we have a car. It's traveling with some initial velocity. When it applies the brakes, it'll decelerate at some rate that's related to its position along its path. And it'll eventually come to rest. Okay. So once we understand the problem, we then try to identify what's given and what we're trying to find. And so looking at this, we're told that the car is initially driving along the road at 60 miles per hour. So that is our initial velocity. The driver suddenly applies the brakes and it decelerates at this rate. And we want to know the stopping distance of the car. So the implication, if we're trying to find the stopping distance, is that the final velocity of the car is 0. It comes to rest. Okay. And again, the acceleration is equal to negative square root of s feet per second squared. Looking at this, s has units of feet. So in order to get a total units of feet per second squared for the acceleration, it's implied that there's a coefficient 1 here that has units that are necessary in order to convert the total into the correct feet per second squared. We could attempt to identify the units of that coefficient and carry them through all of our calculations. Instead, what I suggest is that we go ahead and get all of the different types of measurements into the same units. So in essence, we'll go ahead and put all of the length in feet and all of the times in seconds. And then we don't have to worry about bookkeeping all of the units because they'll come out correctly. So in order to keep the units consistent, we need to go ahead and change the units of our initial velocity from miles per hour into feet per second. So the way we do that, we can do dimensional analysis. We recall we want to cancel those miles, and we can recall that 1 mile is equal to 5,280 feet. And then we want to convert the hours into seconds. So we put hours in the numerator, and an hour is equal to 60 minutes, and 1 minute is equal to 60 seconds. And so together, there are 3,600 seconds in 1 hour. So the hours cancel, the miles cancel, and we're left with units of feet in the numerator and units of seconds in the denominator, just as desired. So if we do that calculation, we get that the initial velocity is 88 feet per second. So that's what's given. We're attempting to find the stopping distance. So we'll go ahead and say that our initial position is 0. And our final position is what we want to find. So we want to find the position at the end, after the velocity has been brought to 0. Once we've done this, understood the problem, written down the givens and the unknowns, we then perform a solution. So in essence, we try to connect what's given to what's unknown. In these rectilinear kinematics problems, these are the 3 basic equations that we're going to use. And so if you recall, we have acceleration as a function of s. We have the initial velocity, the final velocity, and we want to find the stopping distance. And so if we look at these 3 equations, the one that relates the sort of things that we have and the things that we want to find is this one. It has acceleration, which we know. It has position, which we're trying to find. And it has velocity, for which we know the initial and final velocities. Looking at this, in essence, we want to solve for s. And so here we have a differential element s. In order to get the total displacement, or the total position, we need to, in essence, add up all of the differential elements. And so the way that we do that is by integration. So we again can remember that an integral is like a sum. This integral symbol can be thought of as an s, and we're summing up all of these differential elements. We can then substitute in what we know. So we have an expression for a that's equal to the square root of s. And we have v dv. Since we are given a as a function of s, we are able to substitute it into this integral and perform the integration with respect to s. This is something that we need to be careful about in general. We could be given acceleration as a function of time. If we were given it as a function of time, we would not be able to use this equation as such. We would perhaps have to use some combination of this equation or this equation in order to integrate it with respect to time. If we were given acceleration as a function of velocity, we would then have to take the acceleration and divide it to the right-hand side so that we could integrate it with respect to velocity. So this is something to always be careful of. What are things functions of, and what are we differentiating with respect to, and what are we integrating with respect to? Okay. So looking at this integral, we could solve an indefinite integral, be left with a constant of integration. In this case, we actually know what the limits of integration are, so we can go ahead and substitute them in. We know that our initial velocity is 88 feet per second. We know that our initial position, we'll define it as 0. We also know what our final velocity is. So we could set the upper limit VF to 0 and have our upper limit here be the unknown that we're trying to solve for. Instead of actually plugging in the upper limit velocity, which we know, we're going to go ahead and solve it symbolically, leave it as a variable, so that we get an expression for position as a function of velocity. And the reason to do that would be, one, perhaps there's another part of the problem where having a function for s would be useful as opposed to just having the number answer of the position at the final state. So, having it s symbolically could be useful in that regard. It could also be useful in that that function gives us sort of something to perform a sanity check on. We could look at the function, does that make sense? We could plug in different velocities, whatever, to see if that makes sense. So keeping that in mind, we'll go ahead and solve these integrals. On the right-hand side, the antiderivative of v, we add 1 to the exponent to get 2, and then we divide through by 2. And then you evaluate it between the limits of 88 and v. On the right-hand side, we can think of the square root as s to the 1/2 power. So again, we add 1 to the exponent, x to the 3/2 power. We then divide through by 2/3. We still have that negative sign. So that's the antiderivative. And we evaluate it between 0 and s. We then plug in. So we substitute the upper limit. So we have minus 2/3 s to the 3/2. And then we subtract this evaluated at 0 at the lower limit. Evaluated at 0, that's just equal to 0. On the right-hand side, we substitute the upper limit for v, which is just v. And then we subtract that expression evaluated at the lower limit, 88. Then we solve for s, which is ultimately what we want to find. In order to isolate s from the left-hand side, first we need to remove this coefficient, so we multiply by -3/2. Do that on the left and the right. We can factor out this 1/2, left with v squared minus 88 squared. In order to get rid of this exponent, 3/2, we need to raise both sides to the reciprocal, 2/3. And so there's an expression for the position as a function of velocity. That could be useful for checking things. In this case, we ultimately want to find the final position, the position when the velocity has reached 0. So since v final is 0, we have -3/4 multiplying -88 squared. So that'll become positive. We take everything to the 2/3 power. We plug that into our calculator, and the final position works out to be approximately 323 feet. Even though we didn't carry out all of the units on all of the different coefficients, we know that the units will work out correctly because we made them all consistent. We made all of the lengths in terms of feet and all of the times in terms of seconds. So that concludes this example.